Electromagnetic spectrum. Season 2, Electromagnetic spectrum. Physics in Necrotic world. Episode 33, telescopes. Welcome, strangers. Okay, so I'm doing a lot of back-to-back recording because I have such a big backlog of stuff I've typed, but stuff I still have left to record, so I'm just recording everything. So, I mean, you can kind of tell because all the episodes are like, yeah, probably getting a bit tired now. Welcome, strangers. The value of a lens is 1 over the focal length. Focal length must be measured in meters, always in meters, okay? For a diverging concave lens, this would be negative. To find a focal length of a convex lens, what you need to do is focus parallel distant light onto a screen, then move it accordingly until you see a small bright spot of light. Be careful not to set fire to anything. I mean, at least not a caterpillar anyways. That was seriously disgusting. All you have to do is get your trusty ruler and measure the distance between the screen and the lens. There are 2 types of telescopes. You have refracting telescopes, which use refraction, and you have reflecting telescopes that use reflecting. Well, they use reflection. Images in both telescopes should have the same features, but not necessarily the same size. The image compared to being seen at the same distance far away. Well, san, which is French for without. I mean, you see my limited French vocab? Yeah, my limited French vocab. Really bad accent. Without, yeah. So, same distance away without, hang on. The image compared to being seen at the same distance away without, that is the sentence. The image compared to being the same distance away without the telescope, without the telescope, is laterally inverted. Laterally as in L-A-T-E-R-A-L-L-Y. Laterally inverted. So back to front. And then larger as in bigger, yeah, we know that, right? Upside down and real, as in it can be projected onto a screen. The refracting telescope uses convex lenses exclusively. Like, it's basically just 2 convex lenses. And the brighter the image, the larger it is, so it does magnify the image nicely, as the convex objective lens focuses the light by refracting it, and the eyepiece lens just refracts it into your eye. That's nice, right? I mean, you have the convex lens, which is the objective lens, and the convex eyepiece lens. Chromatic aberration, so color blurring, you can get that in some glasses too if they aren't well made, is caused by different colors refracting by different amounts. Big lenses of the refracting telescopes need specialists to make, as it's very hard work. They have to be physically massive discs. All modern astronomical telescopes, as in for visible light, are reflecting telescopes, as they are more budget friendly in their build, and their telescopes simultaneously reflect all frequencies of light the same, so naturally corrects for any chromatic aberration. They can also be chromatic aberration as in color blurring. They can also be made larger for bigger magnification. The concave primary mirror focuses light with reflection larger. The concave primary mirror focuses light with reflection. So larger is like better. Larger as in better because higher resolution. So sharper, better, see better quality image. Did I say better yet? The convex primary lens? No. It was a concave primary mirror and then a convex eyepiece lens. The convex eyepiece lens magnifies the image. It's smaller generally in terms of the ratio, so it can have higher magnifications at smaller physical sizes than refractive telescopes. So that's a nice evolution, right? Evolution of telescopes. What a lovely museum piece. See you next time at Physics in Necrotic World. This is your host, Rimona Christian, out.